Hello, everyone. Let's talk about two sections today. We're going to talk about sections 4.5 and 4.6, which is going to be identifying and performing translations and also talking about similarity. Now, we don't usually do two sections at the same time, but these two sections are very closely related, so they're going to fit together great. So let's see if we can dive in. So the first part is dilations. Dilation is going to be the actual last topic that we are going to talk about as far as our transformations are concerned. We've already talked about translations, rotations, and reflections, and dilations are our very last one. A dilation is going to be the same thing that happens to your eye when you go to the eye doctor and you get your pupil dilated. It is a transformation in which your figure is going to be enlarged or reduced with respect to a fixed point C. So usually when people think about dilation, they think about their pupil dilating and enlarging, but it can also be a reduction as well. A dilation is going to preserve the shape, but not the size of your figure or your pre-image. A dilation is a non-rigid motion. Now it's got to be non-rigid because when you're talking about rigid motions, that is when it is going to preserve both the size and the shape. And so that is an important piece right there. This one is our first one and only one that is going to be non-rigid. It is not an isometry. That is going to lead us to our next piece, which is similarity transformations. So when we have been translating, rotating, and reflecting, we have been creating congruent figures, but now we're not. They're going to be bigger or smaller than the original figures, and so that means they are going to have similarity rather than congruence. Similarity transformations are going to be a dilation, or a composition of rigid motions like translations, reflections, or rotations, and also a dilation. Anything that's going to involve a dilation is also going to involve similarity. The reason that we're going to say that it's similar is, once again, they are going to have the same shape, but not necessarily the same size. To break that down a little bit more, what that means is that their angle measures are going to be preserved, but the segment lengths are not going to be preserved. So you are going to get longer or shorter segments, but the angle measures will stay the same. Scale factor. So because all of this growing and shrinking is going to be based off of a fixed point C, there is a scale factor that is going to determine how much it's grown or shrunk, and that's called the scale factor right there. Sometimes it is represented by the letter K. Okay, so now if you want to find out what the scale factor is or utilize it, there's a little bit of work that you can do that's going to help you out with that. So if you're calculating your scale factor, you're going to create it by building a fraction. And this fraction is going to be based off of a couple of measurements that have to do with length, not angle measures. So when we're talking about our lengths, we want to make sure that we're doing our image on top and then our pre-image on bottom. Remember that your image right here is the second one. This is the final product. So that is going to be where the primes are going to be on the labeling. The pre-image is going to be the original picture, which is going to be where there are no primes at all. And that is going to be how you're going to calculate your scale factor right there. So that fraction right there will reduce, and that'll give you your scale factor. Okay, so now when you're looking at the value that you come up with after you do your division, there's kind of two options that are going to exist. One option is that your K value will be bigger than 1, and one option will be that your K value will be between 0 and 1. Okay, so now when I say bigger than 1, what I really mean is that it is going to be an improper fraction. And so that means is that when you're looking at this fraction that we were talking about earlier, there is going to be a big number and it is going to be on top. And then there is going to be a small number or a little number, and that is going to be on bottom. So that is how you're going to get a K factor that is greater than 1. This is when you're going to be enlarging your shape right there. So the image is going to be big and the pre-image is going to be small. If you end up with a K value that's between 0 and 1, we're talking about very small numbers. So this is going to be a small decimal, or most likely a small regular fraction. And so with this one, the rule is basically flipped. To make the number or the fraction small, you need to have your little number on top and your big number is going to go on bottom. And so that is going to work. This rule right here about image over pre-image is always true, but sometimes the image is the big one and sometimes image is the little one. And so that is helpful information to know as well, just in case you get a little confused. All right, so let's try a couple of problems out, and I think that that'll help kind of clarify things. So here's our first one right here. It says find the scale factor of the dilation and then tell whether the dilation is a reduction or an enlargement. So for our first one that we have right here, what we have right here is we're looking at two triangles. that are next to each other, and then you have your fixed point C right here. And that is causing the shapes to change their size. Okay, so now one of the first things that I like to do is I really kind of like to make sure I pay close attention to my labels. What I see is that I have something labeled P right here, and then I have another thing labeled as P prime right there. So when most people are going to look at this, they might think about starting from the center and then growing, growing, growing as they move outwards, but that's not actually the case. What we are doing right here is we're starting with P, which is our pre-image, and then we're going to be shrinking down to P prime. Prime is always going to be your final product right there, or your image. So this guy right here is actually going to be a reduction. So now that's actually the last question that they had asked about, but it's the first one that I like to answer because it kind of keeps me on the right track. Okay, so now to build my fractions, I've got some good hints for you. You need to take a look at a couple of distances. So our first distance that we're going to look at is from C to C prime, or P prime, which is going to be labeled right here as 4. And then I'm also going to look at the distance from C to P, or from the fixed point to the pre-image right here. And that distance is much longer, it's 12. Now, this is why I like to know that it's a reduction. Because it's a reduction, I know that my fraction should be small on top and big on bottom, and that's definitely the case right here. So I know that I didn't make any mistakes with my numbers. They're in the right spots, and they're going to work out well. Okay, let's reduce it. 4 over 12 reduces, and it's going to reduce down to 1/3. Once again, it's a reduction, so you should have a nice small fraction for your K value, and we do, so that works out well. Okay, your turn. See if you can try the next one on your own. Okay, so for this one, what we're going to do is once again look at the two letters that we have right here. P prime, that's going to be your final product, and P is going to be your pre-image. And so that means we did start off small and then we grew to a much bigger shape. Okay, so now that makes it an enlargement. Okay, also for our distances, we always want to start off with that image on top. So we're going to go all the way out to the prime one. Our distance to the prime was 25, while our distance to the original pre-image was only 10. So it's 25 over 10. Once again, this is an enlargement, so it should be big over little, and it is. And when you reduce it, it is going to be 5 over 2. Another kind of comment to make about this figure that I really enjoy right here is you kind of get to decide what the picture is. So when some people are looking at this original P image and then the P prime, what they see is they see a small segment that grows into a much larger segment. And so you can see that right here. Another way to look at this is with the figure, or the fixed point C right here, is actually part of a triangle that also includes point P. So you're looking at a small triangle that includes both points P and C. And then when you dilate it or enlarge it, what's going to happen is that the dilation is going to stretch this far wall out, but it will still be a triangle. It'll still start at C, it'll reach all the way to P prime, and then the triangle will close off after that. So that's kind of two different techniques right there. The fixed point C can live outside of the figures themselves, or the fixed point C can be a part of the figures themselves. All right, now let's see if we can go in kind of the opposite direction. So right here for our second example, it says triangle ABC is the pre-image. So we're starting off here, and then determine if this is an enlargement or a reduction, find K, and then the scale factor, and then find the value X. So now this time what's happening right here is that you'll notice that there is no fixed point. You could actually kind of find it if you wanted to, by kind of creating a couple of those lines like we had up here in this drawing right up here. And you could find that the fixed point is going to live somewhere out over here, but that's not necessary. In the last problem, we did use that fixed point because we were measuring the distance from the fixed point out to the image and out to the pre-image. This time what we're going to do is we're actually going to use the side links themselves. So what you want to do is you want to find corresponding or matching side links. And so right here, what you're going to find is that what we have right here is we've got these two sides that are on the left. They're not the same exact length, but that's okay because we're talking about a dilation, but they are certainly related to each other. Okay, so now let's see if we can use those to kind of build our shape. So I know that I'm starting off here with ABC, and then I'm going to be changing it to DEF, and it looks like ABC is smaller and DEF is larger. So that means I am talking about an enlargement. So I know that I'm going to be dealing with that. Then that's going to help me set up my scale factor or my K value. I know because it's an enlargement, I want the bigger number on top and the smaller number on bottom. So I'm going to use that 18 on top, and I'm going to use that 12 on bottom. We're going to reduce that fraction a little bit, and that's going to give us our improper enlargement fraction, which is going to be 3 over 2. Okay, cool. So now that covers a lot of the bases that we were talking about. Determine if it's an enlargement or a reduction, check. Find the K value, check again. The scale factor, which is going to be the K value, and then right here, find the value of X. Okay, so now this is where we're going to kind of change gears. Now what we need to do is we need to figure out exactly how long that side is right there. Okay, so now that side right there is associated with this 9, and then the 9 has been enlarged and it becomes this new side right over here. So you can deal with this in a couple of ways. The easiest way is to take the 9 and to multiply it by our scale factor. So that works out really nicely and easily. Now, multiplying by fractions might not be your absolute favorite thing, but it's really easy to do, especially without a calculator. All you need to do is just multiply across the top and multiply across the bottom. I'm going to treat my 9 as 9 over 1. And when I do that multiplication, I'm going to end up with a 27 on top and a 2 on bottom. Easy peasy. This isn't common denominators. It's not all that tricky stuff that you have to do with addition and subtraction. Just straightforward multiply across the top and across the bottom. If you like to write it as a decimal, and I know that many of you do, you can divide a little bit and that'll give you 13.5. This is a little bit nicer because you can kind of compare a little bit and understand exactly what you're dealing with. What was once 12 grew to 18. What was once 9 grew to 13.5. So that should feel a little bit better for you. Okay, example number 3 is yours. See if you can find the scale factor, decide if it's an enlargement or a reduction, and then find the value of X for this one right here. All right, example number 3, if you take a look at this guy right here, we are going to be taking a look at this shape right here. And what I'm noticing is, once again, I have a P and a P prime, and P is out here on the big shape, and then P prime is on the smaller one. It is a reduction. So because it's a reduction, when I'm setting on my fraction, I want to have small over big or a little over big. So I've got my distance right here to P prime, which is 5. And then I'm going to use my larger distance, 10, on the bottom, and that's going to reduce my scale factor down to 1/2. Okay, so now here's the tricky part. What has happened here is that to find our value for X right here, there's a lot going on. So the first thing is that X is your starting value, and you need to multiply it by the scale factor to produce the 4.5. So if you take a look at what I have right here, X cut in half gives me 4.5. So I'm going to actually set up an equation right here in blue, and I'm going to need to solve that guy right there. It's pretty clear and easy to follow. If you took your 4.5 and you cut it in half, you'd end up with a very small number, 2.25. This side right here, we already know is got to be longer than 4.5. So cutting it in half really doesn't make any sense. The picture will guide you. And so instead, if you take a look when I'm solving this guy, instead of multiplying X by the scale factor, which I can't do, I'm going to use opposite operations to get rid of it. So I'm going to take this guy and I'm going to multiply it by its reciprocal, which is 2 over 1. And that's going to give me a longer value, which is what the drawing is going to kind of dictate. And so 4.5 times 2 over 1 is going to give us 9 right there. So that one is a good one for us to take a look at right there as well. Okay, let's move on to the backside. So on the backside, what we're going to do is we're going to change things up a little bit by having you draw the graphs yourself. So what we have right here, for example, 4A, is we have a triangle PQR, and there's a couple of points. Now, I've already graphed mine, but you might need to take a couple moments to graph yours. And what we're going to do with this guy is we're going to create a dilation with a scale factor of 3. Now, 3 is a big number, so I know that it is going to be an enlargement. So I'm looking to create a big triangle. If you wanted to think about it as a fraction like we were on the front side, that's 3 over 1. And so that's going to give us, once again, big number on top, small number on bottom. Okay, so now how can you do this enlargement? I'll show you 2 different ways. So the first way is definitely the easiest way, which is the table. It's no brainer, but you do have to actually create the tables, which a lot of people don't love. So I have created a table by copying down these 3 points that I have right here. And what I'm going to do is I'm going to use the scale factor of 3 to create a second table. And this is super, super fast and easy. All you need to do with your scale factor of 3 is apply it to the X values and apply it to the Y values as well. So you're going to multiply that scale factor on both left and right side, on the X values on the left and the Y values on the right. So we're just going to go down through each and every one of these numbers and multiply them by 3. 0 times 3 is 0. 1 times 3 is 3. 2 times 3 is 6. 2 times 3 is 6. 0 times 3 is 0. And 2 times 3 is 6. Bingo. You've got yourself a beautiful table, and all you need to do now is just graph those points and you'll have yourself a good dilation. Okay, so now what if you didn't want to make the table? What if you just wanted to do it on the graph? Well, this can be a little bit trickier, but this is a pretty good problem to do it with. So I'll show you how to do that. All right, so now what we're doing right here with our scale factor is we're taking this image of this small triangle and we want to grow it, and we want to grow it with respect to a fixed point. Now, if there is no fixed point that is mentioned, the fixed point that you're going to assume they're talking about is the origin. So this is going to be our fixed point that we're going to be growing in terms of right there, okay? All right, so now here's what we're going to do. What we're going to do is we're going to do some measuring from that fixed point out to the points that we already have. So the distance from this origin to point P. This is a really simple measurement right here. It's vertical and it's going to be 2 units. Okay, so now what we want is we want to triple that. So what we're going to do here is we're going to take that distance of 2 units and we are going to recreate it 3 times in a row, and that will tell us where our new point is going to be located at, which is going to be P prime. So P prime is going to live right there. Now I can do the same thing with Q. Now from the origin to Q is exactly 1 unit to the right. Okay, so now we want to once again triple it because our scale factor is 3. So that means we're going to recreate this same distance 3 times in a row. And when we do that, we will get our new location for Q prime. Now R is the trickiest one. Let's see if we can deal with that. So because R is kind of out here in the first quadrant, what we're going to do is we're going to measure from the origin out to R, but we need to measure it on the diagonal. So we're going to be taking a look at this measurement right there. Now this one is definitely a little trickier than the other, so you have to be extra careful when you're doing this one. So we've kind of crossed through these 2 squares on a nice clean diagonal, and that's how we got to R. And once again, our scale factor is a scale factor of 3, so we want to do this 3 times in a row. So we're going to have our first one, then we'll have our second one, and then we'll have our third one, and this will give us the location of our new point that we're going to have, which is going to be R prime. Now, if you take a look at the 3 points that I've created, they match with the table exactly. This guy right here is going to be P prime, which is 0, 6. This one right here is going to be Q prime, which is 3 units over and 0 units up. And this guy at the bottom here is going to be R prime, which is 6 units over and 6 units up. So I have created the exact same image, and I've done it 2 ways. So now one way maybe is a little longer to write down, but definitely very easy to calculate, which is the table. The other way, you don't have to write down as much, but it is a lot trickier to take advantage of. Okay, so it's your turn. So what I have for you right here is a couple of examples of problems to try out. And so we're just going to do them one at a time. So let's start off with this guy right here. Here's a couple of hints, and I want you to try that one out. Here you go. So you've built the table already, and then what you want to do is you want to use your scale factor of 0.5. So this is going to be a reduction in size. So we're shrinking it down, and you can see our small triangle living inside of our bigger triangle. This would be a lot harder to do with the graph. So it's better to use the table for this one. Okay, next, let's try the one that's right after that, which is going to be letter C. This one's got a couple things going on. So you'll see your scale factor is actually -1/3. I want you to see if you can use that guy. And once again, I've kind of given you a hint. You've got your tables all set up right here for you. All right, so if we are following our tables, what we can see is we can see that they are multiplying everything by -1/3. And when you do that, you're going to start off with your pre-image, and then it's going to go to your image, which is not surprisingly much smaller considering how small of a fraction that we had. But there's also something else that's happened. What else has happened to this triangle other than shrinking? What did the negative sign do when we applied it along with our scale factor of 1/3? All right, next one that I want you to try out right here is example number 5. And so see if you can give this one a try. This is a story problem. It says you are using a magnifying glass that shows the image of an object that is 6 times the object's actual size. The image of a spider seen through a magnifying glass is 13.5 centimeters. Find the actual length of the spider. So once again, we're going to be working backwards on this one. Give it a shot. Okay, so you can see my awesome drawing right here. Here's my magnifying glass. Here's my original spider, or my pre-image, and then there is the magnified version of the spider, which is the image. So what I'm going to do right here is I'm going to measure my image, and what I'm going to get is 13.5 centimeters. Now, if I saw a spider that was actually 13.5 centimeters, that would be terrifying. And so what the spider is actually happening here is much smaller than that. So our scale factor we know is going to be 6. And so we're going to use that scale factor of 6 to figure out how small the original spider was. Now, you usually take the original length and multiply it by 6 to create the 13.5, but we're working backwards this time. We're going to use opposite operations, and we're going to divide by 6 on both sides. And that means that the spider is actually a much more attainable 2.25 centimeters long. That's okay. That's not too bad. That's not too scary of a spider. So now, once again, if you had taken your 13.5 centimeter spider and you multiplied it by 6, you would have ended up with a giant spider. And I know that you know that that's not going to exist. That's not a realistic spider. So you can use the actual context of the problem to decide if something is reasonable or not. And you should try to take advantage of that when you can. Let's take a look at example number 6 right here. So now example number 6 right here is going to be about a segment. So we have segment AB, and the 2 endpoints for the segment are listed right here. I've already drawn mine and I've built my table for it. So now the reason that I wanted to go over this one with you is because I want you to notice that it's actually got 2 parts to it. So there is a reflection that we need to perform and a dilation that we're going to perform as well. So let's see if we can do both of those things. So the reflection is listed first, so we're going to do it first. So I'm going to use my tables in order to create this reflection, and I'm also going to use my tables to create the dilation. So let's see if we can take a look. So for our reflection is reflection over the y-axis. I have my foldable right here. For a reflection over the y-axis, I know that what I need to do is I need to change the sign on all of my x values. That's not too difficult to do, so we should be able to do that pretty quickly. So my x values are now going to be -12, and you can't have a -0, so that one's going to stay the same. Now, for a reflection over the y-axis, the y values themselves actually stay the same, so we're going to keep those without changing them at all. All right, correct. Now for our second piece, which is the dilation. For our dilation, what we need to do is we are going to multiply everything by 1/3. Now, please don't go all the way back to the original problem. That's a bad idea. What you want to do is you want to work off of what you've already created. So we're going to take these new values that we just created with our reflection, and those are the ones that we're going to multiply by 1/3. So when you do that, we're going to take things like -12 and multiply it by 1/3, which is going to give us -4. We're going to do 0 times 1/3, which is going to be still 0. 6 times 1/3, which is going to be -2. And -3 times 1/3, which is going to be -1. Okay, so now even though we've created 3 tables, we only really need the very first one and the very last one. So this is the one that I am going to be graphing right here. This is going to be giving me my A prime prime and my B prime prime. So let's see if we can draw that. -4 units over, -2 units down. So if you take a look at my scale right here, I've counted by 2s in order to cram in that point that is 12 units over. So 4 units over is right here, and 2 units down is right there. That is going to be A prime prime. Okay, next, B prime prime is going to be 0 units over and -1 unit down. That is going to be right here. Okay, so you can definitely clearly see that the segment is much smaller. It is 1/3 the size. You can also see that that kind of downward tip that used to be going from right to left, or from left to right, is now going from right to left. And so that you can see that reflection taking part as well. One of the kind of surprising consequences of this problem, because it is centered at the origin right here, is that it also kind of looks like it's been translated up a little bit. So you might have assumed that the reflection and the dilation would have created a image that may have shared the point B with B prime prime and maybe looked a little bit like that, but that's not the case because it is centered at the origin. Even though the center is not mentioned, you're just going to assume that it is centered at the origin. Okay, let's see if we can go backwards. Let's see if we can determine what 2 things are going to create this image based off of the pre-image that you have provided for you. So the 2 pieces that I'm seeing right here is going to be a reflection over the x-axis. So what was once going to be this trapezoid right here is now going to be kind of flipped upside down. And you can see that most easily with the lines X, Y, and QR. And so those guys are definitely flipped. but I also noticed that one of those trapezoids is quite a bit larger than the other. And so I want to create that dilation effect. And so what's happening here is that I'm going to do some measuring. And so the first piece of measuring that you can do is you can measure the distance once again from the origin down to a point like Y. And then you can take that same kind of measurement, but up to the point R, because they're going to correspond. Now, when you do the measurement from R, you're going to see that the distance is now twice as big. So that's going to be a nice, easy one to take advantage of. It is harder to measure on these diagonals, so I don't know that I would necessarily choose that as your first measurement to take a look at, like the measurement to W and then the measurement to P, but it is definitely going to be consistent. You can do that if you would like.